In this video, I'm going to talk about quantum mechanics. Quantum mechanics is a branch of physics that studies the nature and occurrences at the smallest scales. What is a quantum? Well, a quantum is the smallest possible discrete quantity of energy or matter, which means a quantized element can only come in quantities of its quanta and the multiples of its quanta. Still confused? Don't worry, nobody gets it at their first try. It actually is not as hard as it seems. We can look through the quantum timeline. That way, it will make it easier to understand the concepts of quantum mechanics. We will start with the discovery of electrons. They are first discovered by J.J. Thomson in 1897 when he conducted an experiment on a cathode ray tube. Cathode ray tubes are sealed tubes of glass where excess air has been evacuated. Two electrodes, a cathode and an anode, is placed respectively at the left and right end of the tube. A high voltage is applied across electrodes situated inside the cathode ray, discharging a stream of particles from the cathode towards the anode. This stream of particles are called cathode rays. He later came to discover that the cathode ray is negatively charged and the particles are named electrons. Without Thomson anticipating, the cathode ray actually yielded more than just the discovery of electrons. It helped visualize the wave-like behavior of light because it shows how light travels through a medium the way it travels to a consistent path. Since they travel like waves, their wavelengths can be measured. This discovery helped Max Planck form his hypothesis on blackbody radiation. What is blackbody radiation? Blackbody radiation refers to a system or object, a blackbody, to and from which radiation is fully absorbed and emitted. The radiation is mostly depicted as light radiation by their wavelengths. The peak of its wavelengths depend on the light's temperatures. The hotter the body, the higher the intensity of its radiation, thus the peak of its intensity occurs at a shorter wavelength. Generally speaking, blackbody radiation helps you visualize how objects at given temperatures occur in different wavelengths, hence distributing different electromagnetic spectrums. Planck modeled different spectral distributions through electron oscillation. The phenomenons of blackbody radiation have left physicists puzzled, as there were no adequate explanation in classical physics to prove it. It is initially thought by Rayleigh and Jeans that the intensity of light radiation is infinite as black bodies tend to absorb energy at full efficiency. They are thought to radiate continuous energy at all frequencies. Planck challenged that hypothesis by implying that such electromagnetic waves are quantized and not continuous. Planck's hypothesis on blackbody radiation provided the basis of quantum mechanics. So, what did he found to be in agreement with his hypothesis? With respect to solving his hypothesis, he proposed that the energy radiated from a blackbody comes in discrete amounts called quanta. A quanta is defined by an object's quantization of energy, a formula by Planck stating that E must equal h times V, where E is the total amount of energy and U, or the V, is the frequency, h is a constant of 6.626 times 10 to the power of negative 34, and V is directly proportional to E. With respect to proving his hypothesis, he visualized it using the quantization of electrons. The idea of electron quantization in itself is visualizing electrons as a wave. Planck's observations yielded strong evidences that electron motion is quantized. Different spectral distributions in a blackbody radiation indicates that photons are light quanta that compose light, meaning that the energy carried in photons comes discrete amounts. Photons were ultimately discovered by Einstein. Effect in 1905, which won him the Nobel Prize. Well, surprise, surprise, his Nobel Prize was not on his theory of relativity, but actually on his discovery of photons. However, Einstein would not have done it if it weren't for Planck's hypotheses on blackbody radiation, where he advanced with the idea that incident energy is quantized in discrete chunks. Photons have properties like that of a wave, and properties like that of a particle. It diffracts and it can produce interference patterns when discreted on a slit. As photons exhibit wave properties, they also behave like a particle, proven by the photoelectric effect. That was proven by Albert Einstein. Photoelectric effect occurs when metal absorbs energy from light that is incident upon the metal, and it is emitted in the form of electrons. This demonstrates photons' particle behavior, because waves would have deflected off of the metal instead. Electrons emitted from the metal have a specific kinetic energy which is unaffected by light intensity. It is defined by the following formula. Ek equals h nu negative phi, where Eq is the kinetic energy of the electron. Planck's constant times the frequency is the Planck's law on quantization of energy. In this case, it represents the energy of photon. Since nu is the frequency of light, can also be defined by c over lambda, where c is the speed of light and lambda is the wavelength of the light, and phi is the work function of metal incident. Given the fact that a photon light quanta makes up light, it travels at the speed of light and is never at rest. The momentum of a photon is most accurately defined by using relativistic equations. The relativistic equation of momentum is defined by the following formula, where p is the momentum of object, m is the mass of object, v is the velocity, c is the speed of light, which is equal to 3 times 10 to the power of 8. In order for photon to have a momentum, its mass must be 0. To find the momentum quantitatively, we can refer to the relativistic energy of a photon, which can be found by the following formula, where E is the energy of the photons, P is the momentum, C is the speed of light, and M is the mass of the photons. Photons are particles that are never at rest. As they are never at rest, they will always have momentum, and to have a real number momentum for photon, its mass has to be 0. From this, we can conclude that photons have 0 mass. Compton scattering further confirmed the quantum theory of light in terms of wave-particle duality. Compton scattering, as experimented by Arthur Compton, is an event where photons, light quanta, of shorter wavelengths, X-rays, are collided with a stationary electron. This confirms the quantum theory of light by demonstrating how photons are quantas and they have energy that is directly proportional to that of their frequency. By the diagram above, incident X-ray, as defined by lambda, collides with a stationary electron. The X-ray becomes scattered and is defined by lambda prime. It is scattered to an angle with respect to the horizontal axis. Energy from the X-ray is transferred to the stationary electron, causing the electron to move by a Compton wavelength. It is defined by the following formula. By that formula, lambda prime is actually bigger than lambda, as the energy of the X-ray decreases upon collision. Since energy is directly proportional to frequency, the frequency of the X-ray will ultimately be lower, hence a longer wavelength. The Compton scattering simultaneously demonstrated wave and particle properties of photons, as it transfers energy to electrons upon collision, like a particle would do, and it also alters its wavelength, proving that it is quantized. By this, we can further visualize the wave-particle duality. Since electrons are found to have wave-like properties as well, the atomic model is also adjusted. In 1913, Niels Bohr proposed the first ever atomic structure that shows respect to the quantum theory of physics. In 1922, he earned a Nobel Prize for developing his model. Prior to the model, the widely accepted structure depicting the atomic system is Rutherford's model. The model was proven inaccurate as it neglects the conservation of energy. By this model, accelerating electrons must radiate electromagnetic energy. In this case, the electron will be drawn into the nucleus and the atom will cease to exist, according to the widely accepted form of atom we know currently. With respect to the inaccuracy of Rutherford's model, Bohr proposed that electrons are in orbits with discrete energy around the nucleus. He suggests that the energy of these electrons are quantized. How Bohr's model differs from Rutherford's is that electrons have a stable orbit that is discrete from the other energies of electrons around them, while Rutherford states that electron radiates energy, so they can interact with the subatomic particles around them. From what we have learned prior, it is undisputed that light quanta exhibit wave-particle duality. But do all elementary particles behave the same? De Broglie's hypothesis suggests that all elementary particles are quantized. This hypothesis is even validated as experiments shows that electrons can behave like waves also. One of the experiments conducted is the double slit experiment, in which electrons are fired to a wall with double slits towards another wall behind it. Results shows that the incident electrons are distributed to the rear wall are in discrete patterns. This proves the wave particle of electrons. From this, we can conclude that Planck's equation applies to all particulate matter, not just light alone.
From what we learned, we can conclude that the quantum timeline is interconnected. Each finding sparked the light for new discoveries that fuels the betterment of the quantum theory. From the discovery of electrons to the dual behavior of particulate matters, physicists have well connected the dots. The further development of the quantum theory will only benefit the future of modern physics, providing a basis for new innovations to come.